Hello everyone, welcome to the second part of the video lecture of the unit first, that is dimension on units in fluid mechanics, that is dealt in the second year first semester of civil engineering department. In the previous video lecture we have already discussed about the basics of fluid, what is fluid mechanics actually means, what are the basic fluid properties. Continuing with that, here this video lecture tells about the rest of the unit. The next property of the fluid says the surface tension. Every fluid is having very important property by virtue of which it tries to minimize its surface area up to its maximum extent. This property is called as surface tension. It is defined as the force that acts on the surface of a fluid that tends to minimize the surface area. The basic cause of the surface tension is cohesion. Therefore, it is mainly the property of the fluids. The difference between the cohesion and adhesion is within the same liquid molecules, the attraction force that is called the cohesion force, whereas the attraction force between the molecules of two different liquids is called adhesion. The shear stress generates in the fluid because of the fluid property of cohesion, whereas the fluid sticks to the other surface because of the property of adhesion. If the cohesive force is more than adhesive force, liquid is not wetting to the surface, whereas if the adhesive force is more cohesive force, liquid is wetting at the surface. This is the reason of the formation of the drop. The reason of water droplet to be spherical is surface tension. The shape of the drop is mainly governed by the two factors. One is surface tension and another one is gravity. Due to the surface tension, an inward force on the droplet surface forces the droplet to contract from all the sides, and the droplet takes the spherical shape. This process continues up to the time when its inward force is balanced by internal pressure of the droplet. Let us consider a small droplet of radius capital R, where P1 and PO be the pressure inside and outside the droplet. Respectively, the excess internal pressure inside the droplet can be given as by the delta P, which is nothing but the difference between the two pressures. If we cut the drop into two halves, the surface tension per unit length of the periphery of the halves be gamma. Consider the equilibrium on another half. Surface tension force will be balanced by the pressure force. Therefore, delta P multiplied by the area will be equals to sigma 2 pi r. Since sigma and r are only taken to be positive value, so that the delta P will be positive. Therefore, the pressure inside the droplet will always be higher than the outside pressure. Well, the same concept goes for the soap bubble also. Formation of the jet follows in the same manner. Similarly, if we go for the concept of the surface energy apart from this surface tension, the surface is assumed to be formed of swapping a line. The total energy of the surface will be the work done in swapping the line along its length against a perpendicular surface tension force. So the tension force will be given by F is equals to sigma into L, and the work done of the energy transferred in the moving distance d will be given by E is equals to F multiplied by d. If we substitute the value of F, the E value will be coming as sigma L into d. Here LD defines the area, therefore the E value comes as sigma multiplied by area. Here a numerical value has been given, a numerical example has been given on the basis of the surface tension and the surface energy. The next is the capillarity. It is also a property by which the angle of contact. What is the angle of contact? It is the angle between the solid surface and the tangent to the surface of the water inside the liquid. For the wetted surface, the angle of contact remains less than 90 degree, and for the unwetted surface, the angle of contact remains more than 90 degree. When a tube of a very fine diameter is immersed in a liquid, the rise or fall in the liquid surface can be observed depending on the wetting and non-wetting behavior of the liquid to a particular material. The rise or fall in the liquid level in a very fine diameter tube is known as capillarity. and this tube is very diameter is L. The expression for the capillary rise we can get if we take a glass tube of a very fine diameter D when it is inserted into the liquid. The vertical component of the surface tension will pull the liquid upward in the tube. However, the weight of the liquid will push it downward, and this process will continue till both the forces nullify each other. If the sigma is the surface tension of the liquid, theta is the angle of contact between the liquid and the glass tube. If h is the height of the liquid in the capillary tube and A is the area of the tube, then the weight of the liquid of height h in the tube can be given as rho g A multiplied by h. Elaborating the value of A that describes the area, the expression can be given like this. The surface tension will act on a whole circumference of the liquid in the tube. Therefore, its vertical component will be equals to this. This cos theta is taken because of the resolution in the angle. For equilibrium, this equation will be coming into picture. After resolving it, we get h value is equals to 4 sigma cos theta by rho gd. The value of theta for the clean water and glass is approximately 0. Hence, cos theta will be comprising for a value of 1. So, the rise of the water in a glass tube will be given by h is equals to 4 sigma by rho gd. And another numerical example has been given. If we take a clean glass capillarity tube of 3 mm diameter has been inserted in the liquid, it has to be found that what is the capillary rise or fall in the liquid. If the liquid is water or mercury, surface tension of the water and mercury is given respectively. The density and the angle of contact has also been given. So, by substituting the given values directly into the formula of h is equals to 4 sigma rho gd, the value can be determined. Since here in the water case, the cos theta value can be taken as 1, therefore the h value has been taken like this, whereas for the mercury the cos theta value has been taken as 128 degrees. The next property of the fluid says the compressibility and the elasticity of the fluids. The fluids can be compressible or incompressible. The mass density of the fluids, especially gases, carries with the pressure and temperature. The compressibility or the bulk modulus of elasticity K is defined as a ratio of the compressive stress to the volumetric strain. The value of the bulk modulus of the water and air at normal temperature and pressure is given by the 2.07 multiplied by 10 to the power 6 kilonewton per meter square and 101.3 kilonewton per meter square respectively. If we consider a piston with cylinder, when the pressure is applied, increase in the pressure if we consider as delta P, decrease in the volume if we consider as delta V, the volume strain will be given as delta V by V. The negative sign here indicates the decrease of the volume on increase in pressure. Here, the K value is nothing but the change in pressure by the volumetric strain. If we substitute the values, we get the expression as this. The volumetric strain per unit increase in the pressure is called the coefficient of compressibility, which is represented by beta. If we consider the fluid of volume V, density rho and mass m is subjected to increase the pressure, so the density and volume changes y amount of delta P and delta V, but the mass will remain the same. Therefore, rho V is equals to m. Here, ultimately, if we resolve the entire thing, the beta value comes as 1 by rho d rho by dp. Therefore, if the density is not changing with respect to the pressure, then delta rho by delta P is equals to 0. When beta is equals to 0, such fluids are called as incompressible flow. When the density changes with pressure, beta will not have any trivial values. So, such fluids are called as compressible fluids. If we come to the another section of the syllabus that says about the rheology of the fluids. Well, rheology is a branch of science in which we deal with the flow of or deformation of the matter under the effect of the applied force. It is mainly related to the effect of the shear stress on the materials which are having the property of the fluids. In the classical mechanics, the solids are considered as those which follow Hooke's law, and fluids are considered as those which follows the Newton's law. When a force is applied on the material, deformation of the material occurs. In solids, if the force is under elastic limit, material regains its shape, but in fluids, if the shear force is applied, it deforms the liquid and viscous shear gradient forms inside the liquid. The shear stress is mainly dependent on the viscosity of the fluids and the rate of deformation. Therefore, on the basis of the fluids are mainly classified into two categories: time dependent and time independent non-Newtonian fluids. Broadly, if we classify the fluid, it can be classified as Newtonian fluid and non-Newtonian fluid. The non-Newtonian fluid again can be described into the two broad categories, that is time independent and time dependent. So this lecture has basically told about what is fluid mechanics, what are the different sub criteria of the fluid properties, with the continuation in the second part of the video lecture, continued with the first unit that told about the different branches of the fluids with some different types of fluid properties. Thank you.